of all, we have to define the variables. So first variable, let's define mass as 1. We have the length of the string, so we have L. That also has 1. Doesn't really matter. They're just constant. I'm going to define the constants first. We have the gravitational acceleration, which is 9.81. We have the coefficient that we use to match the pendulum system, or like a real life system. So that's the retarding coefficient. I'm going to say that something like 0.2. We also have the time we run the simulation for. We have that for 15 seconds. And now, this is the important part. I said before that I'm gonna make time as a discrete variable. And so, what would each duration of time be? I'm gonna set that as duration, the duration of time for each, I say, discrete value, and that's gonna be 0.101 seconds. And then we have the number of iterations of that time. And so if you have 15 seconds, our iteration, the number of time we repeat, or the number of discrete values we have, is going to be 15 divided by 0.01, which is 1500. And so we have time iter, or t-it, as t divided by t durations, the number of durations. And then we have the angular quantities. And so first of all, we have the angular position, or theta. That's going to be equal to, I'm going to set that as a vector. That first of all, I'm going to assign because I have to declare that vector, I'm going to fill all of them with zeros. And so it's going to be a column vector with time iterations and 1 row. And so that's a column vector. And then I'm gonna do the same thing for the angular velocity and the angular acceleration. And so all of them would be a vector with 1500, so 1500 rows and 1 column, because it's a column vector. And then I'm gonna have a variable for tension. I'm gonna say it's tension. That's gonna be equal to a column vector with 1500 variables, because that's also a variable that's gonna change by time. And I'm gonna assign my initial quantities. And so I'm going to have the first value in my angular position as equal to pi divided by 2. I'm going to have the first variable in my angular velocity as 0. It's going to start at 0, as well as my angular acceleration. It's going to also start at 0. Now, I'm going to also graph the energies, how the energies of the system change. And so I'm going to have kinetic energy. That's going to be equal to this. First, I'm going to declare the kinetic energy also by a column vector, a blank column vector with 0. That's going to be my potential energy and also my mechanical energy. And for those values, I won't have to assign any value yet, because I'm going to do it inside my loop. So I'm going to loop my code for the number of iterations I have, because I'm going to get a timestamp. I'm going to get 1500 dots in the graph, and keep in mind that this code over here is not going to be the simulation, it's going to be the graph. Then I'm going to do the actual simulation after I do the graph. Get a better visualization of what really happens and how the quantities change, how the variables change. So first of all, I'm going to have angular position. I said before that so the angular position at a value 1 plus the before value is going to be equal to the angular position. It's going to be I of the before value plus the angular velocity of the before value. I would have to multiply the duration, because it's going to be, we know that S is equal to UT. So the position is equal to the initial position plus the velocity, and it works the same for angular quantities or linear quantities. It doesn't really matter. But the point is that it's going to be equal to the initial quantity plus the velocity times the duration. So S is equal to SO plus UT. And then I'm going to do the same for the angular velocity, and for the same principle I'm going to get angular velocity times I plus the I's value, the before value. So the after value is before value plus angular acceleration of before value times the duration, which is 0.01, and get angular acceleration of 1 plus 1 of the after value. And now here I'm going to use the equation I derived before, whereby I got angular acceleration was equal to minus g times the sine of angular position, so theta of the same value, so I plus 1, divided by the radius minus the retarding coefficient, so c times angular velocity of I plus 1. That's going to be this here defines the angular acceleration. And then I'm going to get the tension. The tension value would be equal to the mass times g times the cosine of theta plus the mass times the radius times the angular velocity of the same value. And I'm gonna do a because I'm gonna multiply a value. I'm gonna square a value, and this is a column vector. Keep in mind that everything here is a column vector, so I'm gonna use dot square 2, because I can't just square a vector. I need to do dot square it. Okay, now then I can move on to my energies. So my energy at a certain value would be equal to 1/2 times mass times the velocity, which is given by the radius times the angular velocity. And again, dot square 2, because that's the square. And I'm going to get the potential energy is equal to the mass times g times the height. Now for the height, I'm going to say that the maximum height is going to be equal to the radius, because it starts at pi over 2. So it's anything, the height will be the maximum height, which is the radius minus L times, using Pythagoras, cosine of theta, which is angular position. And why is there? Oops. I think it's a problem. Okay, and then we get the mechanical energy, is equal to kinetic energy plus the potential energy. Here there's no semicolon. Okay. And that's the end of my loop. And so now I have to do the graph. So I get this figure, and I'm gonna create 3 graphs. So here and here and here. And so I'm gonna use a subplot first. So subplot of the first subplot, I'm gonna plot the time on the x-axis, the angular position on the y-axis, and then I'm gonna use blue color for that. And in my label for y, I'm going to say it's going to be equal to the angular position. So angular p, angular position, and that's going to be in terms of the radian. And the title of that, of all these 3 graphs, so I'm gonna add the title at the end. The title of them would be the angular quantities. And then I'm going to create another subplot, and now it's going to be the second one. And that's going to plot the time, now the angular velocity. I'm going to use green, and label the y-axis as angular velocity, give the radian, per second, of course. And the title I already wrote at the start. And then I'm going to plot another graph, which is my third graph, with the time, the angular acceleration. I'm going to use black, blue, green, and red now. And the y label would be the angular acceleration in terms of radians per radius per second squared, obviously, because it's the acceleration. And now all of the x labels of this graph would be, because I set here the duration as 0.01, I would have to multiply everything. The units must be in terms of 10 to the minus 2, because one duration is 0.01. And then I'm going to make another figure, and now it's going to be, now it's going to depict the tension and compare it with the weight. I'm just going to do the tension. And so I'm going to plot the time, the tension, and I'm going to use a magenta color. And now keep in mind that, because all of these here, they're column vectors. And when I plot, they must be in row vectors. And an easy way to do this is just to add a simple sign like this. And this basically converts a matrix or a vector. It flips it 90 degrees, or I'd say it switches the row and the column. So a column vector with only the column would now be a row vector when I do this. And for the same thing here in the tension, I'm going to have to convert it into a row vector. And then in the x label, we do the same thing, and now it's going to be 10 to the minus 2 seconds. And then the y label would be tension with a unit, so newtons, and the title would be tension function. Yeah. And I'm going to add a legend that says this is the tension. Or not. called off. And then I'm going to make my final graph, which depicts how the energy is changed. So I'm going to plot the time, the kinetic energy again. I'm going to switch it into a row vector, and then I'm going to use black color, or blue color. And I'm going to plot for the same thing the potential energy and use cyan, or blue and red, looks good. And then I'm going to plot the mechanical energy, and I'm going to use a green. And I'm going to use the X label again with 10 to the -2 seconds. And the Y label as the energy given by joules. And then the title, energies. And now I'm gonna add a legend because there are 3 in one graph. So I'm gonna get the first one in chronological order. I get kinetic energy, potential energy, and mechanical energy. And now that's basically it. So when I run this, hopefully it's gonna give me 3 graphs. Oh, what? Oh yeah. Hopefully when I run this, it's gonna give me 3 graphs. Run. Oh wait. I'm gonna add here all, close all, and CLC. To be clear. There's an error at line 50, figure. What? Why is that wrong? I'm going to do the debugging and come back. So now, I believe everything works. This is the code. I'll post the code in the description below, so you could have a go at doing the same thing with MATLAB. And so when I run this code, I'm hopefully going to get three graphs. Yep. Figure 1. Yeah, like that. So that's figure 1, whereby the angular quantities, the angular position, the angular velocity, and the angular acceleration, how they vary by time is graphed. And also have that for tension. So this is how tension changes along along time, the iteration. So keep in mind that I had 1,000, and I changed the values a bit, but you can see that I had 1,000 iterations because I have 10 seconds and 0.01 per iteration, and so I would have to multiply 0.01, just 10 to the power of minus 2. Oh wait, the power sign is not being printed, but anyways, you can see that, yeah, I would have to multiply 10 to the power of minus 2 to every number to get 1,000 into 10 seconds, and then so on. Do the same thing for energy. Now, as you can see, the total energy of the system is decreasing. And that's because I set the value here. I had this retarding coefficient. And so due to this retarding coefficient can be due to a lot of reasons. For example, air resistance, or maybe heat generated in the string. But anyways, what you can see is that due to that energy loss of mechanical energy, the total energy here, the green, which depicts mechanical energy, and also you can see it by the maximum values of the kinetic and potential energies. that the total energy in the system is decreasing over time. And have a look at this, and I'm gonna make the duration for 15 seconds. I'm gonna decrease. Now let's just leave that as 10 seconds. And when I decrease the retarding coefficient from 0.25 to 0.1, you're going to see a difference. And also, when I look at all the three graphs would now be different. And if I analyze these graphs over here, you see that when the angular angular position, which is theta, is at maximum, so it's not changing, the instantaneous change is 0. You can see that when I track down, the angular velocity therefore is 0, because the change in angular position is 0 at that point. And when the change is maximum, whereby the gradient is maximum, you can see that there is no change in the angular velocity, and so it's equal to 0. And you could do the same thing. You could track the part where angular velocity changes 0, go down, and you could get that angular acceleration then is 0. And when you get to the point where the change in angular velocity, the change in angular velocity is maximum, you could track down and see that the angular acceleration is 0. And so I'm going to make, and also the tension graph, you can see that tension is keep decreasing due to that retarding coefficient. And so, if I make a change to, it was 0.25, but now I'm going to change this value to 0.1. And notice how the graph changes. I would hopefully get a graph that would have a slower rate of decrease in both tension, in all the variables, tension, mechanical energy, and the angular quantities. And so here, you could see that the decrease in total energy, mechanical energy, in the system is decreasing, but only at a slower rate than before, whereby the value for C, the retarding coefficient, was 0.25. And the same thing for tension. You can see that the rate at which these are decreasing, the values, are slower than what it was before, as well as here in the angular quantities. You could see, you could have, in the graph before, when I looked at the angular acceleration, the graph was something like this. But now you can see that the maximum values of these angular quantities don't really change, although before they changed quite a lot. So yeah, those are the graphs, and now I'm going to move on to making a new script, and now I'm going to actually make the simulation part. Okay, so moving on to the simulation. First of all, before I code the part for the actual simulation, because I'm going to use the same variables that I used before, I'm just going to go here and then copy all of the variables. Now keep in mind that I won't need a tension, so up to here, I need the angular quantities, and I would also need the first values. I won't need the tension because the tension does not play a role in defining the motion in terms of the angular quantities. I'm only going to use the angular quantities. Well, so we do the same thing. We do we set the loop for t iteration number of times, and then we do the same thing. We first of all say, well, then the angular position of n plus 1. So the angular position and the next value in the angular position for every iteration will be the before value plus angular velocity of the before value times the number of the yeah, 0.01, which is the short amount of time. And then we do the same thing for velocity and acceleration. This is going to be velocity, this is going to be acceleration, it's going to be acceleration. And for acceleration, now we do a different thing. We use the equation we got over here. So I'm just going to copy what we have here. I could have copied all of them, but yeah. All right. And then I'm going to plot. And I forgot setting up the video. So here I'm going to set up the video. So I'm going to write v equals, I'm going to open video writer and say name as pendulum movie .avi, and then I'm going to have to set the frame rate. I'm going to set something like 50 or 60, and I'm going to open the video. Right, so now next onto the coding again. I'm gonna simulate. First of all, I'm gonna make the background. I'm gonna make a white background. So I'm gonna fill. Keep in mind that it's gonna take quite a time. Gonna have to fill. So I'll come back after I do the coding part. Run. When I press this, it's gonna show a figure. Yeah. And now I would have to leave this on for quite a long time, because as you can see here, when I press the AVI file, it's 1.3 megabytes now. And when I press it again, it's gonna have increased, yeah, to 1. Now it doesn't let me touch it because the size is keep changing at 1.99. So I would have to run this for it's not going to be 10 seconds, although it theoretically has to be, because there is compiling time, and that takes quite a long time. And so after about 30 seconds, I'm going to stop. Or when this pendulum here stops, I'm going to download this file and see how it looks like on the video. So I'll come back when it has stopped. Big, as I imagined, is 3.29 megabytes. And so what I'm going to do is I'm going to go to home, and I'm going to download. Then I'll go to here, AVI. This computer, I don't have any software that could open an AVI file. So I'm going to have to convert it to MP4. That's what I did before in testing. And so when I select file, and I choose this over here, so pendulum movie bracket 1, that's here. This is the same file as I just downloaded. And so when I open that and press convert, it's gonna give me a video file that I could open to see what happens. So did I mention this? You could go to the description below, and you could download, or you could see the code I have written here, and use that for you to do in your own MATLAB software, in your own MATLAB. Yeah. So this is a 12 second long video, and you can see the pendulum works. And because I only ran this video for 10 seconds, it doesn't really show how the pendulum is gonna, how this over here, this retarding coefficient would have an effect on the system. But yeah, that's it. You could, set this as 100 seconds, and you could see how you'll be able to see how the pendulum really goes. Its displacement reduces as it goes. But yeah, you could do that. You could adjust the code in any way you want. I'm gonna post these on the descriptions below, both the graphs and the simulation movie. And so yeah, that was it. That was my first video in MATLAB, my introduction to MATLAB, and I just done simulation, a simulation of a pendulum system. Thank you very much. Please leave a comment below if you want to give any suggestions. Please like and subscribe. And thank you. That was me, Joe's Physics Corner.